Okay, hey guys, so I just want to show you how to find the reactions on here very quickly for number one. Problem one, actually it would probably help if I showed you what the problem is first for future reference. This is problem one, and it is asking you to draw the moment and shear diagrams and equations. And for the deflected shape, don't worry about getting equations. For the deflected shape, just do what the professor was saying in class. Make your deflected shape, or just draw what you expect the deflected shape to be based on your experience and on what the moment diagram looks like, basically. Okay, so here is my work. I normally don't show this, but the reactions are fairly simple. Okay, it's just one page, and my handwriting is horribly messy and like size 20 font. So when you do this, you should be able to finish this in like half a page. So there's really not that much to the reactions, but I think that the tricky part is just figuring out what do you do with this vertical member and what do you do with this hinge. Now to do this, I'm just gonna draw my diagram first. And unfortunately, this is not to scale. I tried to draw this to scale, but it just takes too much time, and my videos always take longer than I would like them to. So this is going to be P equals WL over 2, and this is L over 2, L over 2, and this length here is L over 2. Okay, now the first things first. What are my equations? You always have sum of force in the x direction, y direction, moment about z, and in this case you have moment about the hinge. For this moment about the hinge equation, like we were talking about for last homework, you only need to look at one side of the hinge or the other, and I should emphasize that this is a hinge. These two are roller supports. This is what we call a rigid connection, and I'll explain what that means later on, or a fixed connection. I'll explain what that means later on, but in this problem, I think it'll be easiest if we start, it's usually easiest if we start with fx, because usually most of our forces are in the y direction. We can get fx very easily. Remember that when we're doing these three equations, these are what we call global equations. That means that we have to look at every force and every reaction when we're trying to use these equations. This moment about the hinge is a special equation. We only need to look at one side of the hinge. In this case, I think it'll be easiest if we look at the left side of the hinge, but let's find fx first. If we're doing fx, we just add up our forces in the x direction. And what do we have? We have ax acting in the positive direction and p acting in the negative x direction. So we have ax. And it doesn't matter that this is offset. Alright, this could be any shape we want at all. As long as we're adding the x components of every force and the y components of every force together, we'll be fine. Ax minus p equals 0. We get ax equals p. And that is our ax. For our ay, like I was saying earlier, I think it's best if we use moment about the hinge and we work with the left side. If we do this, we're going to have that, let's say that this way is positive. We're going to have, from the hinge, we have ay acting this way, and we have a distributed load acting this way. So we have ay times L, this should be an arrow, not an equal sign, this should be an arrow, ay times L minus WL, that's the total load, times L over 2. That's the distance between the middle of the load and the hinge. Right, so the centroid of the load is at L over 2 from the hinge. The centroid of the load is right here. And this is the total load, so this is P equals WL. I should not use P. I should just say that this force here is W times L, and it acts some distance L over 2 away from the hinge. If I solve for this, I'm going to get rid of L, I'm going to get AY equals WL over 2. And that is my second reaction. Now, my next reaction, if I do sum of forces in the Fy direction, I'm going to have Cy and Dy unknown. I know what Ay is, I know what my loads are, I don't know what Cy and Dy are, so using the force in the y direction will leave me with two unknowns, and I'll have to use the moment equation. If I start with the moment equation though, I can eliminate one of the unknowns. If I take the moment about d, dy will not enter my moment equation. Let's try it. I'm going to try taking the moment about d and see what I get. I should be able to get the moment at Cy directly, the force Cy directly. Okay, so in this case, if I do moment about d and I do positive, I need to consider forces on both sides of the hinge. That's what distinguishes this from my my hinge equation where I only looked at one side. And in this case, I have Ay acts at some distance 2L away from d. I have Cy, which acts at some distance L over 2 away from d. I have this distributed load, which is WL, and it acts at a distance L over 2 plus L over 2 plus L divided by 2. Right, I need to look at the middle of this load, the location of the centroid. So this is going to be 3L over 2. And I also have to take this force into account. This force is WL over 2, and it acts some distance L over 2 away from D. Now if I rewrite all of this and I know what AY is. I do not know what Cy is. I'm trying to find Cy, but I know everything else. And I'll let you do the math here, but you should get Cy equals 3 over 2 WL. Now I can use my sum of forces in the y direction, and I'll get AY plus CY plus DY minus WL equals 0. And from here I should get DY equals negative WL. This negative sign just means that this arrow is drawn in the opposite direction. In other words, technically the force is pointed downwards, but I don't need to change anything. Because I know that the force dy has a negative in it, I do not need to change the direction of my arrows in order to keep my signs positive. I can just keep the negative in my reaction force. Okay, so we have this. Now let's try drawing diagrams, and let me just check my notes here. Okay, so I'm going to draw the diagrams for CD and DE, because I think going around this corner here is what is confusing a lot of people. Like, how do you draw diagrams in a 2D shape? Basically, what we're going to do is draw this the same way that SAP 2000 draws diagrams. And we do that by just drawing them directly on the frame. So before we go there, let me where did my notes go? Let's just look at what we have. I'm going to make my cut here and here. Maybe I should do this in red. I'm going to make my cut here and here. I'm going to look at this section, the top side, and I'm going to look at this section, the right side. In class, we've normally been looking at the left side. In the last few homework problems, we've normally been looking at the left side. In this case, I'm going to look at the right side and see, because the right side, it's easier for me to look at this side than it is for me to look at all of these forces. At least I think it's easier. Your mileage may vary, but I think it's much easier to look at the right-hand side or the upper side. It might be easier, instead of looking at this vertical end, let's just rotate it. Let's pretend that we're rotating it so that we're looking at something like this. If I draw that out here, we have something that looks like this is our force P equals WL over 2, and we're making our cut here. We have a shear force and we have a moment force. our shear force is going to be V of x, and our, hopefully my markers don't die on me here, it will be m of x. And my equation is just going to be V of x plus P equals 0. V of x equals negative WL over 2. There's no x term. In other words, my graph will be constant. If I look at m of x minus px, right? The force times the distance. This is x. My x is starting from here. Minus px will be 0. M of x equals L over 2 times x. Now when I draw my diagrams, and this is going back to what we were doing in the first video, which you should have watched, we are looking... I'm going to try and line up... Let me draw this again here. You should always try to line up your diagrams. So we have P, and this is D, this is E. We have shear on the right, and shear is positive this way. Our shear is negative WL over 2. So we go down here. This is what our shear diagram looks like. And it goes down to negative WL over 2. If I draw my moment, this is my shear. My moment diagram looks something like this. Let me draw my moment diagram upside down, just to mess with you. This is going to be WL over 2x. I'm going to draw my graph. This is a positive equation. My positive is downwards here, right? Because my arrow is downwards. So when I do this, I should get something that looks like this. That is my positive graph. Okay, so that's all good.